Hi, everybody. I hope you're all well. Today we're going to continue our conversation, our discussion of graph theory. We're going to take it in a slightly different direction. What have we done so far? We started out by talking about Euler circuits, the bridge problem, the bridges of Königsberg. And then we moved on to talking about all kinds of different things. We talked about planar graphs and hypercubes last time, kind of jumping around the map in terms of subjects in graph theory, because really what I want to do is give you an overview into kind of just how wide a variety of problems graph theory helps us answer, and I don't know, maybe provoke some interest into the subject, because even if, I mean, like I've been saying, even if applications of math are really what you're concerned with, this is one of those subjects that there are so many fun questions, both pure and with and applied questions. And I know that I've been focusing a little bit more on the pure side. If you're wondering what pure math consists of, it's these hypercubes and all this stuff that we don't necessarily relate to the real world. But today, I wanted to start off the lecture by talking about some applications of Euler circuits to the real world, and then Hamilton, things that are called Hamilton circuits or Hamilton paths, and have different but very important applications to modern science. So we'll talk about that today. Some applications of Euler paths in circuits. Yes, and then second thing we're going to talk about is something called the traveling salesman problem. And I'll put in parentheses Hamilton circuits. Good. So, where to start? Right. So I have this. I have an example, a real-world example of Euler. What do I want to say? Eulerization. This is what we call it. Okay. So I'm gonna start. Well, I'll introduce it. We shall consider a UPS driver. Although we may replace the UPS with any other. We could have postmen who need to walk up and down streets. We could have policemen who walk a beat. Yes, although a UPS driver could be replaced. So although UPS could be replaced by a number of different services, i.e. postman, police, yes, etc. And we will try to find an optimally efficient route. Okay, so this is a slight variation on we're no longer going to say we need to go down every street exactly once, like we needed to cross every bridge exactly once in the bridges problem. Note here we are not saying that every street exactly once. Like in the bridges of Königsberg. Okay, and so here's the map. And we're going to have, I have it saved as an image. Good. So here is our UPS driver. Oops, cancel. Okay, and so we want to optimize the route that starts at this point right here and ends at this point right here. So given that we've been studying graph theory, I guess I'll start by just showing you some routes that the UPS driver could take, and then I want to turn this into a graph, and I'll show you how we can do that in a pretty simple way. Good. So what are some different routes? If our UPS, we wanted our UPS driver to, he has to, every street on this map has a house on it that our UPS driver has to drive down, right? And so we want to find, except for maybe this Parkview Road, maybe there's no reason for the UPS driver to drive up there. But on each of these blocks, the UPS driver has to drop off some packages. So the goal is to have him drive every street as few times as possible. So the first question is to ask, do we have an Euler circuit? Well, I don't know. Probably not, right? Just looking at it, we had a pretty... see, now I can't go down there or there. We had a pretty surefire way of knowing when a graph has an Euler circuit, and that's precisely when every vertex has even degree. Now, if we look at the street corners as our vertices, we can already pick out some that have odd degree, right? This one, this vertex, this corner, has only 3 streets coming off of it. So we already know that once we get to that corner, and then leave that corner, and then come back to that corner, we're stuck. We now have used all 3 edges. And similarly, if we start there, and then leave, then at some point we have to come back, and then we leave, and we can't get back. But that's okay. I guess if we want to start here and end here, what was our condition for Euler paths? Was that we have 2 vertices of odd degree. So maybe I'll write that here. Notice that if an Euler path exists, i.e. a route from start to finish, which uses each street once, each. Exactly once. Then this is the, or rather, an optimal route. I.e. a best case, or a shortest. root. Okay. And so if that, so how do we know if that exists? We recall a graph G contains an Euler circuit if and only if every vertex has even degree and also G why don't I do this as separate ones? G has an Euler path if and only if exactly two vertices have odd degree. So if you want a reminder on that, you can look back on our past lectures or lecture notes, because I discussed both of those theorems in depth. Here the vertices will be our street corners, the street corners. Intersections of streets which are our edges. So what does this mean? If I look back here, this means that there is an Euler path if and only if exactly two street intersections have an odd number of streets coming out of it that the UPS driver needs to go down. So here are the vertices. So the UPS driver can find an Euler path if and only if are two intersections. Here, why should I? Here. Exactly two. On his route. So exactly two intersections on his route with an odd number of streets coming out of them. That the driver must take. Maybe not the clearest way of saying that, but I think you get the picture, and I'll draw the picture. I'll draw the picture for you right now. So, let's take this thing and I'll copy it down here. Copy. And paste. So what I want to do is I want to turn this into a graph. Okay? So how am I going to do this? Well, first I'm going to mark every intersection that has streets coming out of it that our driver has to take with a dot. And I'm going to put the first dot in red. I'm going to, yes. So this will be our starting and our ending vertex. Okay? So why don't I say start, and here end. Okay. Now I want to make vertices at all of the other street corners that have streets attached to them that our driver must go down. Okay, so he's got to hit all of those streets. Maybe he doesn't have to hit the school district. Let's say that. Okay, just going along, putting dots at intersections. And like we said, I guess he doesn't have to go around the park. That would be silly. But maybe we'll put that in as an edge that he could take. Yeah, it won't be helpful. Okay. Now I want to draw edges which represent all of the streets that he has to go down. So I'm going to draw an edge like there, and an edge like that. I'm not going to do this straight line tool. Just going to draw them like this. An edge like that, an edge like that, an edge like that. I'll stop saying that over and over again and just draw the edges. Shoop, 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 shoop. As I do this, these are known as grid graphs, actually. There is a type, a specific kind of graph known as a grid graph, which is exactly what it sounds like. In graph theory, we like to give names to our graphs, and we like to name them according to what they sound like, or look like. So we also have caterpillar graphs, and I'm sure you've all heard about trees. Good, I think I've got all the edges there. And we have grid graphs like I'm drawing here. We also have lobster graphs. We have claw graphs. All very fun things. We have stars. Fun names for graphs. Here, I'll go back to the side remark. Graphs have fun names. I should say some graphs have fun names. Some graphs have fun names. Depends on how fun you think these are. A graph like this is a grid graph. We have caterpillars, or I'll do stars first. We have stars. Stars have one vertex in the middle, and then it just connects out to lots of different vertices. We have caterpillars. And caterpillars have what we call body vertices. So that's a path that goes like that. And then they have some number of legs coming off of them. Right? And so we call this a caterpillar graph, even if it has a funny number of legs. Yeah. And I guess it kind of looks like a caterpillar. I'll come back to that when we have more fun names. Okay. And so now, actually, what I want to do is draw the graph, and then I want to actually erase. I want to erase the background. I wonder if I can do that. Delete. Ooh, lovely. And so here we have our graph. And it's missing a little connection there, but So the question becomes, how do we turn this into a real thing? Okay, so what I actually want to do is copy this. I'm going to go back and put the little map there so that nobody gets lost if you're just reading the lecture notes. And then I'm going to paste our graph. So we use this graph to look for Euler paths okay. And what we find is, so let's count. What we want to do is we want to count all of the odd vertices. So we'll say this one is going to represent an odd degree vertex. Okay? So let's do that highlighting. So which ones? We have this one, that's an odd degree. We have this one, that's an odd degree. We have this one, that's an odd degree. All the ones on the boundary, really. See 1, 2, 3 edges coming out. This is 1, 2, 3, 4, so that one's okay. 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay, just looking for boundary vertices with 3 edges coming out. Good. This is funny that we have our start and end points are at very funny places. They're at even degree vertices, but oh well. Okay. Is that all of them? I think so. All the ones in the middle are gonna have degree 4, right? And this one has degree 4. This one has degree 4. 2. Okay, I think we got them all. Oh, no we didn't. We're missing one. I'm sure you caught that before me. Alright, so now we've done all of our odd degree vertices. And what do we find? So if we know that, remember, G has an Euler path if and only if exactly 2 vertices have odd degree. And so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we have 14 vertices with odd degree, so no Euler path exists. We don't even need to look for it. And see, if you didn't have that theorem, which might have seemed obvious when we stated it, you might have spent some time looking for a path, for a way of doing this really optimally. But what's going to be fun is we have a really easy way of optimizing this route. But we can still find an optimal route. We do this by Eulerizing the graph. That should be a U. Eulerizing the graph. And what this means, this just means connecting pairs of odd vertices until exactly 2 vertices are left with odd degree. if we want a path. Then a circuit. And remember that a path is just an Euler path means we take every edge once and we start at one place and end at another. An Euler circuit means that we take every edge once and we start and end at the same vertex. Good. Okay. So I'm going to again copy this graph. And so an Eulerized version copy. Okay, so now we're going to take a little blue pen and we're going to connect pairs. So the first thing that we're going to want to do is connect all the ones that are close to each other. So we're going to want to connect those two. And we're going to want to connect these two. Because what these connections are actually going to mean are just going down the same street twice. We don't always know. Maybe he'll have to go around some blocks sometimes. But yeah. So let's make this connection. Okay. And then we'll make this connection. Now, I'm going to make this connection. Actually, I'm going to do this. Because we have to kind of jump. We can't go straight. He can't drive straight through the block there. So he's going to have to jump. And so again, we're trying to do minimal amounts of jumping. But this is how I'm going to do it. So I'm going to connect those two because that's just a one jump, we might say. But this one will be a slightly longer jump. Although we now have two vertices that are of odd degree. Remember the park. So let's add this one, the park, right, which goes to there, and then we'll make another one going to there. Okay. I shouldn't draw those arrows. Remember, we have the park here, and so he can go around the park, and that's a more efficient way of doing it. And now our start is an odd vertex, and we have, so I can do, yeah, this odd vertex left. So we still have 1, 2 odd vertices. But we want him to end at an even one, which is not going to work. Remember, the start and end vertices are our start and our odd degree vertices, right? So this just means connecting pairs of odd vertices until exactly 2 are left with odd degree. I will erase this vertices. Start and finish are left with odd degree. Because remember, those are the only ones. If you want to look back at the bridges problem, you can kind of remind yourself why. You have to get out of because from the starting vertex, you have to leave. You're going to have to come back, and then you leave again, so you want it to have odd degree. Exactly the opposite of the Euler thing that we were doing. So what are we going to do? We're going to connect these two odd vertices, and that'll make this one even and this one odd. So let's say that he's just going to jump along. We'll find the shortest route from here to there. Okay, here's what I'm going to do. I think that this will be better. I think that what I'd like to do is draw one like that. So now we make the end vertex odd, and we make this one even. And then we'll do a jump along like that, and then we'll do a jump along like that. Good. And now we've got it. Now we have exactly two that are odd. Perfect. And now we know that we have an Euler path. Let's see if we can find it. Okay. So, blue. So I'll make a remark here for those who aren't listening to the video. Note blue edges indicate either retracing a street or taking an alternate route as in the park. And what's fun is that we know that we're guaranteed an optimal strategy by doing this sort of thing. And if all of our odd degree vertices lie next to each other, and we can just do this kind of choop choop, that's just going this way along the street and then returning back along the street, even when he doesn't have to. If we can connect all of our vertices by just like single edges like that, that's optimal. If we could have connected all of our odd vertices by doubling single edges, then we would know this solution is optimal. At the moment, I'm pretty sure that it's optimal. I gotta say, I haven't proved this one, but these problems get a little tricky quickly. So as a final thing, before I move on to traveling salesman problems, let's find a route. Okay, so now let's find a route. Copy. Let's find a route. Paste. Okay. And I'm going to get rid of some of these other things because they're kind of annoying me now. We don't want to confuse ourselves with more things than we need to. I mean, graph theory is all about simplifying problems because, as we know, relatively simple problems can feel confusing quite quickly. So, okay. And so now remember that our two odd vertices are start and end. Okay, so how am I going to do this? I'll use red, and I'll kind of go along here and I'll find one. And what am I going to do? I'm going to use Fleury's algorithm. Using Fleury's algorithm, i.e. stay close to home whenever possible. Okay, so that's what I'm going to do. I'm going to take this street. I know that I'm going to have to cross every street exactly once now, right? I know I now know that an optimal solution uses every edge, blue and black, exactly once. That should be a parentheses. Wow, I'm failing at writing today. Okay, so let's do it. So I want to take this one out. He's going to go down the street there. Then I can't go back home, so I go out to here. And then I still can't go back home, so I go out to here. Now I can go back to a previously visited vertex, that one. So I'm going to do it. I'm going to go there, and then I'm going to take the blue edge back out, which, remember, is just retracing a street. Now, can I go back home? No. But maybe I'll stay close to home, and I'll go out along this street, and then back along this street. And then I'll go out along this street, because I can't go back to home again. And then I'll go up this street. Now I can start going back towards home. So I'll go to back there, and then up here, around there. And now, notice now that this whole section is kind of, it's done. And we're that much closer to our ending point. So, now, staying close to home, let's go back down here, back along there. Previously visited vertex, now we have two choices. We visited that one, and we visited that one. So what am I saying is that it doesn't matter. Let's go down here and not walk the same street twice like that. Now, can't go back to any previously visited ones, so we'll do this one. Can't go back to any previously ones, so we'll do this one, and then this one, and then this one. Okay, now we can go back to this one, so let's do that. And now we can go up here, we only have one shot. We can go back to that one, so let's do that. Up there, out here, and down to that one, over to that one, down to this one that we've seen, up again to this one that we've seen. Now over here, over here, over here, over here, over here, etc. I think you see how this is going. Now we'll go down here, back there, and then back, and over here. And do you see how this is just working out seamlessly for us? We go up here, we go back there. That's because I caught the problem in our textbook. Haha. And I go over here. Now I can go back to this vertex that I've already seen. Over here. Down to this vertex I've already seen. I'll go over here. Maybe I'll go down here and kill these guys. And now I'll go up to this one that I've never seen. Then I'll go back over to this one that I have seen. There. Over to here, because I've seen him. And I'll go back that way. Then I'll go over here. And then down, and I do those two blocks. Okay, and so we know that this is an optimal solution. So, the fact that he was a UPS driver was kind of unimportant. It was that he had a fixed start and a fixed end place. It wasn't necessarily the most efficient fixed start and end place. You know, if we had been able to pick those, we could have chosen different start and end points, which were more efficient. But I don't know. This is what we were presented, and we found an optimal solution to the problem. If we used the smallest possible number of blue edges, then we know this is optimal by nature of the problem. The driver must go down every street. So the only thing we can really change is the number of blue edges we used. Okay, so next. What if the driver wanted to visit specific points, vertices, rather than roads? And this is what we'll call the traveling salesman problem. And this is all going to come straight from your text, or not straight from your text. Of course, it's still my rambling, but this is chapter 7. I believe. No, chapter 6 of your textbook. Chapter 6 of text. Note that Euler things came mostly from chapter 5. Okay. So I'll stop the video here and I'll start a new one.